Hello and welcome. In this video, we will be using PyMOL 3 to inspect biochemical structures and start thinking about the science of what we want to display. By the end of this tutorial, you'll be able to apply and inspect object-specific PyMOL presets, understand the importance of structural inspection and preparation for scientific storytelling, load crystallographic density maps into PyMOL, and identify some key differences between a prepared and unprepared protein structure. Let's get started. Open PyMOL 3 and fetch the 5IEY structure using either file getPDB or by typing fetch 5IEY into the command input area. We can see a small molecule, in this case an inhibitor, bound to the protein structure of the cyclin-dependent kinase CDK2. To learn more about the 5IEY structure, be sure to take a look at the PDB entry on rcsb.org. And to get hands-on with this structure as part of a structure-based virtual screening workflow, check out the Introduction to Molecular Modeling in Drug Discovery Schrödinger online certification course. In the previous video, we introduced objects and selections and had a brief look at some of the coloring and styling options within PyMOL. It is important to be able to show off interesting parts of a structure or molecule in order to successfully communicate science in a useful and engaging way. In PyMOL, applying a preset can be a quick and efficient way to apply, show, hide, or style common features, such as secondary structure, solvent, or polar interactions. We can think of presets as time-saving rendering recipes. Using the Action submenu next to our 5IEY object, let's try out some of the presets. Classified has removed the water. Simple has swapped out the cartoon for a ribbon backbone, and we have the option to do that one with or without solvent. Ball and stick has done what's expected and displayed all atoms in a standardized ball and stick representation. B-factor putty is a measure of uncertainty of an atom's position. The thicker red tube high B-factor regions here indicate greater displacement from the average value. These regions typically have higher flexibility and lower electron density. The technical preset has the protein chain ribbon colored blue through red, and the polar contacts, yellow dashed lines, have been generated and added as a new object which we can toggle on and off. The ligands preset is similar, but instead of all polar contacts being displayed, only those that are between organic molecules or ligands and other atoms in the object are displayed. We can see the protein in ribbon representation with interacting side chains as wireframe lines and organic molecules as licorice sticks. The ligand site cartoon preset is similar, but with a cartoon rather than a simple ribbon backbone, so we can get a better idea of the protein's secondary structure here, alpha helices and beta sheets. The rest of the ligand site presets add different types of surface, so you can get an idea of the contours and shape of the binding pocket. Nice. Pretty, with and without solvent, is a cleaner version of the ligand site cartoon preset, no side chains or polar interactions. Publication, again with or without solvent, uses a different or fancy cartoon representation setting where the helices and sheets have grey insides or edges. We'll look at protein interface in a later video with a different structure that has some protein-protein interactions. And finally, default is a basic wireframe. Styling our 5IEY structure with the various presets has revealed a couple of things about the structure and the limitations of some of the presets. For example, some of the polar interactions that were displayed as part of the ligand sites cartoon preset don't make a lot of sense, as some of the atoms implicated in these interactions, such as the protein backbone atoms, are hidden. You may also have noticed that our structure, the protein, the water, and the inhibitor molecule all have no hydrogen atoms. We could cleverly use selections to display missing backbone atoms, or commands like unset deep to turn off the sidechain helper for a cartoon representation. We can even use other tools within or outside of PyMOL to do things like add missing hydrogen atoms, but the key message here is that it is important to be aware that edits might be needed before we can best show off our science in PyMOL. Due to the nature of 3D structural determination methods, a lot of PDB entries do not include coordinates for every single atom in a structure, and some atoms within a PDB entry may have multiple sets of coordinates. For example, flexible regions and hydrogen atoms are often not observed in X-ray crystallographic experiments, and therefore not included in the PDB coordinate files. whereas many NMR structures, such as the 2-HIU insulin structure we saw in the PDB 101 session file in the first tutorial, is an NMR structure with various states. You can learn more about structural determination methods via the RCSB PDB training portal and their guide to understanding PDB data. We can see in our 5-IEY structure that there are multiple copies of some of the side chains, for example asparagine 132. There are also a couple of binding pocket waters that appear to be in very close proximity to one another. I'm using the measurement wizard to calculate the distance. This seems a little too close, especially considering that there are no hydrogen atoms modelled here. To further inspect our structure, we can load in a crystallographic density map, a 2FOFC map. We can do this via the File Get PDB panel or by specifying the file type with the fetch command. In this case, fetch 5IEY, type equals 2FOFC. Let's use the wizard menu again and choose Density Map Wizard. Here we can left-click on any point in our structure to center the density map. As well as trying out the options in this menu, we can use the Selection Mode menu in the Action toolbar to increase or decrease the scope. Test this out with chains versus atoms or residues. Some objects, such as density maps, polar contacts, and measurements, don't contain atom coordinates and have different options in the ASHLC submenus. But since they are objects, we can still toggle them on or off to include or exclude them in the workspace. Take some time to inspect asparagine 132 and notice that there are coordinates for water molecules in the 5IEY object that don't appear to have any density. Water positions in X-ray structures are not always reliable. Let's check out a prepared version of the CDK2 protein and compare it to the current structure to get a better idea of how we might want to edit or prepare a PDB structure before, for example, running further molecular modelling experiments, inspecting polar interactions, or creating a publication-worthy image. Come up to File, Open, and choose the 5IEY Prepared PDB file from the PyMOL 3 course data directory. This is the same inhibitor-bound CDK2 structure that we downloaded from the protein databank, but it has been prepared using the protein preparation workflow in the Schrödinger molecular modelling environment Maestro. Let's save or update the session name by coming up to File, Save As, and naming this session 5IEY Prepared Comparison, or by typing the save command followed by the session name and PSE extension in the command input area. In the Contents panel, we can use the All object to apply the technical preset to both the 5IEY objects. We can see by toggling on and off the two different objects that the prepared structure has had hydrogen atoms added, and that the protein, ligand, and solvent atoms have undergone a gentle energy minimization, as the atom coordinates generally overlay well with the original structure, but there are some small shifts in the locations of the prepared atoms. As we saw earlier, sometimes the electron density may be inconclusive, or may indicate that a particular side chain, like asparagine 132, has a 50-50 chance of being in one position or another. When preparing proteins in Maestro, we can use a number of methods to inspect and assess side chain orientation, and we can choose to commit a specific side chain in its default or alternate orientation. Hydrogen bonds are one of the most important types of interactions in proteins and protein-ligand complexes, so adding back the hydrogens that we know should be present in a structure is often extremely valuable when we want to communicate our scientific findings. Hydrogen atoms can be added within PyMOL, but they're added according to heuristics with no understanding of global pH, local pKa, or the orientations of neighbouring hydrogens. The protein preparation workflow in Maestro, on the other hand, takes global pH and local pKa into consideration, and optimizes hydrogen bonding networks when hydrogens are added. Let's do a comparison by adding hydrogens to the PDB structure by clicking on the Action submenu next to the 5IEY object, choosing Hydrogens, then Add. Take some time to compare the locations of the hydrogens in the unprepared PDB structure and the prepared 5IEY structure. Also, notice the difference in applying presets per object and using the all object. It can be important to use object-specific commands if you want to see object-specific features, such as polar contacts. We'll be exploring how to display specific polar interactions in the next video, so more on this soon. That brings us to the end of this tutorial. You can now apply and inspect object-specific PyMOL presets, understand the importance of structural inspection and preparation for scientific storytelling, load crystallographic density maps into PyMOL, and identify some key differences between a prepared and unprepared protein structure. Thanks for watching.